Hello, everyone. Just want to give a quick recap of magnetostatics. So this material is supposed to come sort of as a wrap up to the lecture 14 notes on vector potential, but it'll go through a little bit of the earlier stuff too. And then I want to give a little preview of lecture 15 as well. So first things first, we started off talking about magnetism by introducing the Biot-Savart law, which was empirical. It came from experiments, and we just sort of wrote it down. And here is the form of it for a volume current density J. It lives up in the numerator. It looks a lot like Coulomb's law for the electric field, except there's a cross product. There had to be something different because now there's two vectors that go into that integral. We have a J vector and a script R vector. And the only sensible thing to get a vector out is to do the cross product. Once we had that lets us calculate magnetic fields in much the same way we calculated electric fields from Coulomb's law. Once we have that, though, we want to get some differential equations, and we can take carefully the divergence and curl of the Biot-Savart law, and we have to be careful with how we treat the script over R cubed. You end up with a delta function that picks out a value of J, and that's how we get the right-hand side of Ampere's law in differential form. Curl B equals mu naught J. The other equation that we get, we take the divergence of B, and we genuinely end up with 0, no matter what current we have. And that's a statement that there are no magnetic charges. So if we had something that looked like div B equals non-zero, that would tell us that there's whatever on that right-hand side is creating magnetic field lines radiating out of a point, just like charges create electric field lines that radiate out of a point. We've never seen one of those in nature, so we set the right-hand side of that equation to 0, and that's equivalent to the statement that there are no magnetic monopoles. The important thing about these equations is that you look at them in comparison with the electrostatics equations. The divergence of E, Gauss's law, is rho over epsilon naught, and the curl of E is 0, which is saying that the electric force is conservative. And as usual, as is the trend in going back and forth between electrostatics and magnetostatics, we swap dots with crosses. So that's what's happened here. The next thing we did, and this is lecture 14, is we introduced the vector potential. So we had the idea that once we have an electric field, boy, it sure would be easier if we had something simpler to work with. And because the curl of E was always 0, we could write the electric field as the negative gradient of some scalar field V. And that was really nice. We had a whole chapter, chapter 3, about all the cool things we can do with V. Well, we don't have curl B equals 0, but we do have div B equals 0. So what can we do with that? The guess is that we can write B as the curl of a vector field A. And that vector field A is called the vector potential. Why can we do that? Well, again, this is just talking by analogy. You can guess that the electric field can be a gradient because the curl of a gradient is always 0. And here you can also guess that the magnetic field is a curl because the divergence of a curl is always 0. And both of these equations work both ways. If B is the curl of A, then the divergence of B is 0. And if the divergence of B is 0, then the curl of, then B can be written as the curl of A. So A is in many ways analogous to the electric potential V, except it's less useful. It doesn't turn B into a scalar field the way that V turned E into a scalar field. If we know V, that's it. We know a number at every point in space, and we can compute the electric field from it if we want to, and it's much easier to work with. On the other hand, if we want to use the vector potential, we still have to know all the components everywhere. And so that becomes a little bit harder to work with. And in magnetostatics, A is sometimes useful, but it's a lot less useful than the electric potential was for electrostatics. On the other hand, once we have the vector potential, we start to talk about some really important concepts. One of those concepts is gauge freedom, or gauge invariance. And this is just the point that there are lots of different vector potentials that we can pick. We could have always picked different scalar potentials, but there's not that much you can do to a scalar potential. You can add a constant to it and get the same electric field, but that's all. Anything that's not constant that you add to V will change the electric field. On the other hand, you showed in lecture 14 that if I add the gradient of a scalar, grad F, to the vector potential, then I get the same magnetic field out. Because when I take the curl of a gradient, that's 0. So if I take the curl applied to both sides of this equation, curl grad F drops out on the right-hand side, and I'm left with curl A prime equals curl A, and I've got the same magnetic field in both cases. Now, there are only so many constants you can add to a scalar potential. That's pretty boring, but there are a whole lot of non-constant functions F. And for every non-constant function, I can have a different vector potential. That's a huge amount of freedom. We call that freedom gauge freedom. It's often useful to pick a particular gauge, so to use up some of our freedom to make the vector potential look a little simpler. And one common choice of that is picking what's called Coulomb gauge, and that's the choice that we set the divergence of A to 0. And you proved that was possible by finding a formula for F to make that true, right? So let's say someone hands you a vector potential that's not in Coulomb gauge. There's a procedure that you developed in lecture 14 notes that you can create a different vector potential describing the same magnetic field that is divergenceless, that is in Coulomb gauge. The reason it's called Coulomb gauge, more or less, is because it makes magnetostatics look more like electrostatics. So things look more like Coulomb's law. And there's a formula for the Coulomb gauge vector potential that looks a lot like the Coulomb's law for V. It's always possible to pick Coulomb gauge. You don't have to, but it's always possible to pick it. And if you do, you tend to get nicer equations. Okay, so that's pretty much it for the big picture of vector potential. It turns out that it's a lot less practically useful than V is, but all of the facts about it that we've developed are important, and they're going to come back later. The vector potential really shines in electrodynamics, and so we're going to need it to do a lot of things involving radiation, special relativity, and time-dependent electromagnetic fields later on. Now for a quick preview of magnetic materials. So magnets are pretty important. Things in the real world are made of atoms, and atoms have little magnetic moments. And so if you think about a little loop of current, it produces a magnetic field that looks something like this, and we call that a magnetic dipole. And we call the magnetic dipole moments little m. This is in direct analogy to the little electric dipole moment, vector P, that created a sort of similar looking electric field. Then when I stick a bunch of those atoms together into a magnet, each little atom is a magnetic dipole, and the whole magnet overall has some magnetization, capital M, which is a magnetic dipole moment per unit volume. And so this is in direct analogy to the polarization P from dielectric materials. And that's the starting point for chapter 6. Lecture 15 notes will walk you through the rest of that chapter. And there's more or less, it's the same ideas. There's a couple differences. All materials more or less are dielectric, but in magnetism, you have both diamagnetic and paramagnetic materials. You end up with having two different signs of susceptibility, positive and negative, and a few other minor differences that you'll develop in lecture 15. So that's it. Good luck on the rest of it. And we're getting to some good stuff real soon.